Okay, good evening, everyone, and welcome to this inaugural lecture event. My name's Roy Taylor. Unfortunately, the head of department, Professor Michelle Doherty, is traveling abroad at the moment, and she sends her apologies for being unable to personally welcome you all, and also to introduce tonight's speaker. Before we begin, I want to provide some essential housekeeping information. So, on the unlikely event that the fire alarm goes off, could I ask you to, in an orderly fashion, please leave the lecture theatre by the doors at the back or the door here, and make your way immediately out of the building following me, and gather at an assembly point. The assembly point is on Exhibition Road, on the corner there with Imperial College Road. I should also let you know that this evening's lecture is being recorded, and it's also being live streamed. So as a result of that, can I request also to respect the speaker and ensure, please, that your mobile devices or your phones are either switched off or at least on silent. Also, at the end of the lecture, there'll be a short period of questions, which Marina will be happy to answer. If you want to remain anonymous, unfortunately, we can't do that in the lecture theatre, so you would have to really ask your question then really online. And they will be given by someone at the front, answered by someone at the front. Okay, so that gets us ready to start. Can I really offer a warm welcome to everyone here in the lecture theatre, and also to those who are viewing actually online. As we sort of slowly begin to get out of the pandemic, we hope, our showcase inaugurals they're really a route for getting back to normal in-person operation in the department, and really a welcome to social interaction. The department really takes enormous pride in these events, and we highlight really the world-leading research and the academic excellence of our professorial staff. So tonight it's a real pleasure for me to introduce Professor Marina Galand. So I have a few crib notes here about Marina. They're all quite good. They aren't, there's nothing embarrassing. So after completing her undergraduate studies and MSc degrees in Strasbourg at the University of Strasbourg, Marina obtained her PhD degree from the University of Grenoble in France in 1996. This was followed by several postdoc fellowships in various places in the United States. But in August 2005, we as a department were very fortunate when she decided to move to the Space and Atmospheric Physics group here at Imperial. In 2008, Marina was awarded the Elsie Widdowson Fellowship and was promoted to Professor of Planetary Science in 2020. So you can see that because of COVID, we've been waiting quite a while to celebrate Marina's promotion. Marina's research achievements are really have been recognized in many, many ways. In 2006, she received the Zeldovich Medal, and in 2017 was elected a Fellow of the Institute of Physics. This was followed by the award of the prestigious Holwick Medal, jointly by the Institute of Physics and the Société Française de Physique in 2018. Marina is really recognized as a world expert in cometary plasmas, and we're really proud of her high research profile. She's a passionate science communicator and enthuses her students with her love of physics. And she also is very active in outreach activities. So that gives you an outline of Marina's achievements so far. We're actually going to hear now really about her science, and it gives me great pleasure to hand over to Marina, who's going to tell us about Aurora in the solar system. Please, Marina.
Thank you very much, Roy. So thank you for joining me today, either in person or online. It is my great pleasure to share with you part of my journey under the auroral skies in the solar system. So first, I am going to define what I mean by aurora. Then I will highlight what aurora can teach us. And finally, I would like to share part of my cometary adventure. But first, what is an aurora? So, oops, on this one. But you can still see, even though it's still quite some light, that aurora is a moving dynamic phenomenon. The first time I saw an aurora, that was during my PhD, when I went to Tromsø, north of Norway. I went outside. It was on the site of the infer radar, away from the town. I went outside. It was dark, pitch dark. It was a snowy landscape, so it was a bit spooky. And then suddenly, I saw this green hand, really literally. And then after a few seconds, half of the sky was illuminated. And that I will speak actually. Oops, sorry. Let me go again. And I said, OK, that's just visible light, you stay there. But it was really impressive. What's going on here? That was less impressive. OK, sorry, we had to switch, actually, from these computers to the others. So I hope there will be no other inconvenience. OK, let me do it from the computer. Yes, so it's dynamic, it's changing all the time, so it can be quite unsettling. So during that first week when I saw for the first time in my life auroral emission, I took picture during the night of the aurora and during the day of the incurrent scatter radar, which was probing the upper atmosphere. And then my mother made this painting combining picture I took during the day and during the night. But you can see the auroral emission can take a large part of the sky. And then from then on, I could understand the folklore around the aurora. Here is an Inuit sculpture which shows the... Oh, yes. OK, I have to look at here. Which shows the aurora, which has decapitated a man. Don't worry. Auroral emissions are not dangerous. But as I can say, if you don't, I just said earlier, if you don't know what it is, as it is changing and moving, it can be quite unsettling. But what is an aurora? So it's emission, light, which is emitted in the atmosphere at Earth above 100 kilometers or 60 miles. And so let's consider here neutral atoms, so molecules in the atmosphere, for instance, N2. And an energetic particle can be an electron, an ion, which collide with this neutral. And this collision can result in an excitation. So an electron goes to a higher energy level. But you can't stay excited forever. At some point, you need to relax, at least to go to a lower energy level. And you can do that through radiative de-excitation, so emission of light. Of course, this process in the atmosphere is not enough to qualify the emission, the light, as aurora. What you need, in addition, is that the energetic particle, at least the original source of energy, which is going directly or indirectly after a chain of reaction going to lead to this excitation and emission of photon, you need that this source of energy comes from particles, electron, ion, or neutral, from outside the atmosphere. So aurora is therefore the photomanifestation, so emission of light, which can be in the infrared, visible, X-ray, ultraviolet, of the interaction of energetic extra-atmospheric particles with an atmosphere. So let's take a few examples here. On the lower right, you have a picture taken on Earth. It's in true color, but the auroral emission shown in the other figures are actually in false color because they were taken in colors which are not visible to the human eyes, namely in the ultraviolet and in the X-ray. So we have here a picture of Saturn and Jupiter. The background picture is a visible picture, but the auroral emission is shown here in white over the pole. And if you look at, from this point of view over the pole of Jupiter, then you can see the auroral oval, and you see a lot of different structure. You have aurora not only around planets, but also moons. For instance, here, Ganymede, it is the largest moon in the solar system, actually larger than Mercury, and it's the only moon known in the solar system to have its own magnetic field. And you have also auroral emission here over the pole. But for a planet which doesn't have a global magnetic field, such as Mars, then there are still auroral emission, but they are not confined to the polar region. There are different types of aurora at Mars, but here it's the diffuse aurora, and so it's present over a large range of latitude. That will be the same at comets. But let's focus for a moment on aurora at Earth. The two major colors are green and red. Green at lower altitude, 100, 180 kilometers, red at higher altitude. Both of those colors are actually emitted by atomic oxygen, but the associated lifetime the radiative lifetime of the excited state is different, and the process to generate those excited states is different, hence the different altitude. The aurora, as I mentioned, is at high latitude. So here the southern aurora, it's over Antarctica. Actually, it's just out of Antarctica, so it's mainly over the ocean. So you have aurora australis over the southern hemisphere and aurora borealis over the northern hemisphere. So over the northern hemisphere, the region where most likely you are going to be able to observe the aurora is shown by this brown this green band here over North America and over the Scandinavian countries here. And I've been lucky to be able to observe the aurora from Fairbanks, Alaska, in collaboration with Dirk Lummertsam from the Geophysical Institute and with Laura Petitcolas, who is a very inspiring person. And also from Tromsø, Norway, and I will come back on the campaign there later on. But why is the aurora located at high latitudes? So here's a schematic which illustrates the sun. The sun is emitting not only photons, light, but also charged particles, solar winds, many electrons and protons. And then this plasma, the solar wind, is going to interact with the magnetic cavity of the Earth. It's a schematic here, but it's captured the main interaction, the fact that the solar winds are charged particles, and in violet, that the magnetic field line of the Earth. And the particle can't just, because they are charged, go wherever they want. And therefore, they can only penetrate this magnetic shield in some very specific region, namely here on the day side and also through the night side. But they can't penetrate over the low latitude region because of the closed magnetic field line. So on the night side, they actually is where you will observe the most spectacular auroral emission because the particle can be accelerated very efficiently, and then they will bombard the high latitude region. Here, the aurora is shown in blue, but as I mentioned, it's just a schematic here. It's in truth is green. And finally, there is one type of aurora I would like to highlight. So I say aurora is induced by the bombardment of particles in the high latitude region. Usually it's electron, but you can have proton. And in some region, proton actually are carrying most of the energy. So a proton-induced aurora, proton can directly excite an atomic oxygen, for instance, leading to the red line. But the proton can also capture an electron and become an energetic H atom. And this energetic H atom can be in an excited state and then de-excite emitted light. And because H atom is energetic, then the light is Doppler shifted. So I led a proton aurora observation campaign in Tromsø many years ago. That was with Supriya Chakrabarty and Jeff Baumgartner, who built the two spectrographs. That was when I was in Boston University. So here I am, arriving alone. It wasn't originally the plan, but for the modeler, it was great. With two instruments, I had to put together and calibrate and have them run over the all winter. But at the end, I managed, and here they are. The instruments are below this dome here, observing the aurora. So we have seen that the aurora is fascinating because it's changing, it's moving, it's dynamic. But beyond the fascination, actually we can learn invaluable information from the auroral emission. So what can we learn? So auroral particles interact with the atmosphere. I just mentioned that that can lead to the auroral emission, but that also can lead to the creation of a plasma. So let's look at that more carefully. So ionization of a neutral by impact by an energetic particle. So again, we're in the atmosphere. We consider a species, for instance, N2, O2. And an energetic particle can collide with this neutral species, and it can lead to an electron which is stripped from the molecule. So you end up with an ion, positively charged ion, and a free electron. So an electric charge medium, plasma, which is the fourth state of matter besides solid, liquid, and gas. But why, even though only a very small part of the upper atmosphere is ionized, it's less than 0.1% in the region where the atmosphere is produced, the aurora are produced, but it's where actually we encounter the most of the plasma in the atmosphere. Why should we care about this plasma? There is a lot of space physics related reason, also prebiotic chemistry relation, but there is also a technological or an impact on our everyday life. Space weather. Space weather represents the condition of the sun, the interplanetary medium, and in the close environment of the Earth and Mars, which can affect human life and human technology. So if this layer of plasma in the atmosphere is perturbed, it's going to perturb communication between satellite and the ground, or it can generate current which in the ground which are going to generate power cut, among others. So it's very important to be able to assess this plasma layer, to characterize it. So where then the aurora come into place? You can, the only way to have a global information about the auroral input and particle input over the auroral region at a given time is to take a snapshot, to take an image of the auroral oval. You could, I mean, you can, and it's done, fly a satellite to measure those energetic particles, but you get the information only along the trajectory of the satellite. If you take a picture, then you can get at given time information about the particle input over the whole auroral oval. So you use the auroral emission to get information about the auroral particle, and then from that, you can derive information about this critical plasma layer. So there are different steps here and type of models, but I will only highlight the first one, which how do we describe our auroral particle undergo a collision and undergo energy degradation. That will be my only equation. I was asked to be as friendly as possible. And so that's the Boltzmann equation. What does it mean? So sorry. So that's a conservation law. And what is the Boltzmann equation telling us? So let's consider a number of particles n at a position r and a velocity v. So we have on the left here the position space, and on the right the velocity space. And we consider all the particles which are in this volume, this violet volume around the position r and the velocity v. The total number of particles, which varies as a function of time, it's the change in the number of particles within those volumes, plus the change due to the fact that the particles have a velocity, so their position is going to change over time, and the fact that those particles can undergo external forces, and therefore their velocity can also change over time. In addition, the volume element itself can actually change if some of the forces are dissipative. But anyway, so on the left-hand side, we have the total change in the number of particles in this volume, and that corresponds to the change due to collision. So if a particle undergo a collision, then its energy is going to change, therefore the kinetic energy, so its velocity is going to change, so it can come into this volume or get out of this volume. And if we apply the Boltzmann equation, for instance, to electron, then at a given position here, you can have suddenly, poof, an electron which is produced if you had a photoionization. So then it means an ion and an electron is produced. And if the electron produced is produced at the position r and velocity v, then it's one more electron in the volume element. So there are other types of models than to describe the plasma and so forth. I'm not going to go into detail of it, but I've been developing such a model at Earth, and I mean only on Earth, but applied to the high latitude, I mean the atmospheric region at Earth and at different solar system bodies in link to different space mission, and with my PhD student and with my research associate, as well as many BSc, MSI, and MSc students. So I cannot show all the results. I will show only one of them. That's at Ganymede. That's work by Gianluca Carnielli. So Ganymede, as I mentioned, it's the only Jovian moon. It has its own magnetic field. And in blue, you can see the magnetic field of Ganymede, which here reconnect with Jupiter. And those little dots, it's the result of a test particle model. Those little dots are the ion. So those ions here, which are produced by electron impact on the neutral of Ganymede. So it's water and O2 mainly. And that's, such a model is critical to be able to explain observation from mission, which spacecraft which has flown by Ganymede, such as Galileo, ongoing mission Juno, and upcoming JUICE, the Jupiter Icy Moon Explorer. But let's come back on what can teach us or what can Aurora teach us, and give one example. So I'm back to now. I'm back to Tromsø in Norway. Remember, had to put the instrument, the two spectrographs together, and we observed aurora from space. And here is the H beta brightness as a function of wavelength, so as a function of color. And because it's in the proton aurora, because the emitter, here it's the H atom, is energetic, that is Doppler shifted, and because most of the particles are coming towards the observer, which is on who is in the ground, then it's blue shifted. So you can use this information to derive the energy flux of the incident proton, and from that then derive the perturbed plasma layer or the level of conductivity, I mean how conductive the atmosphere is going to be. And that is what is shown here as a function of the mean energy of the particle. And we see that for proton, being given a given energy flux, protons are a lot more efficient to ionize and to allow the atmosphere to be conductive than electron. And so it's very important to characterize and identify the proton component of the precipitation. Now, similar emission can be observed, auroral emission can be observed in different solar system bodies. We saw H alpha in the UV, that would be H Lyman alpha at Earth, and we can use this emission to infer information about the energetic proton which precipitate. But if you go to another planet, for instance, Jupiter and Saturn, you will also observe Lyman alpha in the auroral region. But because the atmosphere is mainly made of H and H2, you will infer a different information. You will infer information about the incident electron. Okay, all the work that I have done, I've not done in isolation, but with many colleagues. And I would like to thank some of my key mentors. So Don Carpenter in Stanford University in California, where I did a summer internship as an undergrad, studying the propagation of very low frequency signal in the atmosphere. Don was a very generous, kind person, filled of humor, and taught me to look at data without no a priori, with really an open mind. I did a PhD in Grenoble, France, and one of my mentors was Wlodek Kaufman, and I have a vivid memory of going in his office and explaining some derivation, mathematical derivation, and being bombarded by a question, and I had really to make sure that I got justified every single aspect. And Wlodek wanted to make sure that there was no stone not which remained unturned, and I'm very grateful for that. Then I moved to Boulder in Colorado. I work with Art Richmond at the High Altitude Observatory, and I have fond memories of our inspiring discussion, as well as my favorite study remains the effect of magnetic mirroring of each atom in the proton aurora. I stay in Boulder and then moved, but work with also Tim Fowler-Well and Dave Evans on the effect of identify the effect of energetic proton in the auroral region using a 3D general circulation model. And I have good memories of the Friday morning donut brainstorming meeting with the whole group. I was in the research side, but there is the operational side where the Space Weather Center, where you monitor and try to predict the condition of the sun, interplanetary medium, and space environment 24 hours a day, 7 days a week. Next, I moved to Boston. I work at the Center for Space Physics in Boston University with Supriya Chakrabarty, studying the Auroral mission as seen from space and from the ground. And I work also with Michael Mandelo on modeling Saturn's atmosphere, upper atmosphere. And I have fond memories working there, and beside the scientific aspect where I learn a lot, I also learn what it means to have a team. And at last but not least, Roger Yale from the Lunar and Planetary Laboratory in Arizona, by the side of whom I have learned tremendously. And working on Titan's ionosphere using the Cassini observation. So it has been, it has been an immense privilege to learn by all of them, to work with them, and to be inspired by them. And I would like to thank them profoundly. But I've also received invaluable advice from women scientists. And I'm highlighting here a few of them in planetary physics. And I'm immensely grateful for having inspired me, being who they are, being actually themselves. Finally, there are also great women scientists in the department. And there are 30% of the academic staff in our research group who are women. And they're representing 45% of women in the department, including our head of department, Professor Michel Dugarty. So now I'm arriving at the last part of this lecture, and I would like to share with you my cometary adventure. So let me move on. So after the first European Space Agency mission to a comet, Giotto, which visited Comet Halley, the Rosetta mission was launched in 2004. And on board, there was the Rosetta Plasma Consortium instrument. So there was a hardware involvement from the department. The plasma interface unit associated with the Rosetta Plasma Consortium, which provide power, but communication and deal with data from the 5 sensors, which are plasma, particle, and field sensor, was built here in the department. And Chris Carr was the PI for operation. But there was no involvement on the science side. So I decided in 2012 to initiate and start and move on Planetary Science. And to do the science I wanted to do, I was also needing to have information on the total number density, neutral and ion composition. So I contacted Katrin Aldweg, who is the PI of the instrument which is measuring those quantities I just mentioned. And she very warmly welcomed me in her team, and I've been working closely with her and Martin Rubin since then. Then, after a 10-year journey and 2 years and 7 months of deep space hibernation, which was actually a first, Rosetta was going to hopefully wake up. So actually, the picture here on the right, it was a picture I took from the screen of my laptop. I was in the living room with my son, and I said, we're going to see Rosetta waking up. And after 45 minutes, my son said, I like you, but frankly speaking, it's not to be long. At the very moment, Rosetta woke up. And then after, in the following weeks, all the instruments were checked, and there was a successful rendezvous in August 2014. And we see here the first movie of the target for Rosetta, Comet 67P. So how big is the comet? So 4.1 kilometer long and 2.55 miles. And for the Londoner, it's from Big Ben to Tower of London. For dimension, so here's a little dot. That's Rosetta. And how big it is with a solar panel is a bit longer than a basketball field. And then as for the core, where you have all the instruments, it's about as big as a standing greenhouse. Some pictures. So on board Rosetta, you had also a lander. It's Philae, which landed in November 2014. And I really like very much this picture, where you see a Philae foot, which at the time, so at 12 years old. And here that's the surface of the comet, which is 4.6 billion years old. Rosetta, of course, also offer us amazing picture. So do you? I don't know if you can see it. I should have mentioned that. So here is a model of 67P, but here it's often referred as a space duck. So you have the head here, the neck. The little duck you had in your bath when you were a kid, and the body. And so here it's a picture of the neck, and you can see a lot of structure. But the picture was enhanced because the color of the surface is really dark. Actually, a comet is darker than charcoal. So unlike the previous Cometary mission, which were just flybys, Rosetta escorted Comet 67P over 2 years, so away from perihelion than when the comet was the closest to the sun, highest outgassing activity, and then away. And it was really walking by it at 1 meter per second. And, but then could attest of the increase in activity and how then the interaction changed with the solar wind. Up to the end of mission, the 30th September, so that was a picture I took from ESOC, and the loop is closed. Now Rosetta had a controlled landing on the surface of the comet, and that was the end of mission. So we wanted to say goodbye. It was a lot of mixed feelings. On the one hand, we were really excited because we had just seen the first data arriving on Earth, and it was the first data ever from the close to the surface. And at the same time, we were extremely sad because, well, we knew it was the last data we would ever have from Rosetta. So there is one study I would like to highlight before to finish this lecture that I did with Rosetta. That was, and of course, which is related to Aurora, that the fact that we discovered auroral emission in the far ultraviolet. So this study was done with colleagues in the US, in France, in Italy, in Switzerland, and in Sweden. So clearly international. And I would like to have a special thought here for one of my dear colleagues who contributed largely in this study, Paul Fedman, who passed away a few months ago. So this auroral emission, again, is not in the visible, it's in the UV. So in the UV, so between the visible light and, but not as energetic as X-ray. And the spectrograph on board the Rosetta detected atomic emission from hydrogen and oxygen and carbon. And so we're wondering how is this, those emissions produced? So when the nucleus is close enough to the sun, then the ices sublimate, so the gas is generated and is escaping the nucleus, but you have those emissions which has been observed within this envelope of gas. So one proposed process was the dissociative excitation. So you have energetic electron which collide with a neutral molecule, for instance, O2, CO2, or water, and then the molecules dissociate, and you can end up with an atom of oxygen or hydrogen, for instance, in an excited state, and then they excite, emitting light. So we wanted to address two questions. Is this process the main process generating those emissions? And if so, what is the source of those energetic electrons? So for the first question, we look into the nadir direction, where we had a well-constrained neutral composition and information about the energetic electron, which were measured in situ at Rosetta. And what we did is that we use observation from energetic electron, observation from the neutral composition and column density, and then calculated the brightness and compare this brightness with independent observation from the UV spectrometer. And here's the comparison for the oxygen brightness. So at 1304 angstrom, the disk and the triangle is 1356 angstrom. The model brightness is in black, and the observed brightness is in magenta. And we can see a very good agreement, but in addition, we can also see that when we were not observing any significant amount of energetic electron, then the UV instrument wasn't observing any significant brightness. So the main process is indeed this dissociative excitation process. So if it is, then what is the source of the energetic electron? And for that, we look through the lamp. And so we were measuring energetic electron in situ, away from the emission, and calculated the brightness. And then we compare with the observed brightness, which was produced, the observed emission, which was produced far away. And so if there is correlation, it means that the source of those energetic electron is large scale, while if there is no correlation, it means it's local. And here is the one example of the comparison. So the H Lyman beta brightness as a function of time over 2 days. So for each of those periods, the column density of the neutral is constant. So the variability is only driven by the energetic electron for the calculated brightness, which is in blue, and then for the observed brightness, which is in magenta. And you can see a very good agreement. So it means that the source of the energetic electron is large scale. And what is it? So it's consistent with what the particle in cell models, simulation have shown, is that those electrons are solar wind electrons, which are accelerated because you need acceleration. The solar wind electrons are only 10 eV. You need 15, 20 eV for generating such a process. And they are accelerated in the environment of the comet through a potential well. So, are they auroral emission? Yes, they are. And more importantly, they can teach us about the solar wind electron variability. But what next? Now that Rosetta is on the ground, sleeping with Philae and never, unfortunately, waking up again. Well, the cometary adventure continues with the third European Space Agency mission, Comet Interceptor, which is targeting a dynamically new comet. So dynamically new, what does it mean? That's a comet which has not been detected, and which, when we will encounter it, it will be its first path into the inner solar system. So we will have the surface composition, the surface will be as pristine as it can get. This mission is not one, but actually 3 spacecraft. The European Space Agency is supporting the mother probe and one of the mother spacecraft and one of the probe, and the second probe is from JAXA. A mission adoption, cross fingers, is next month. So we are leading the flux gate magnetometer on the probe B2. And the instrument team includes Emanuele Cupido, Chris Carr, and Irene Ruiz Rodriguez. And we are also in close collaboration. This work is largely complemented by the team at the Institute of Space Research in Graz. And I guess I will move on because I think I am well over. So cometary research, yes, I'm doing it, but I'm trying also to share it through outreach activity. And I've been focusing here on research, but a large part of my time here is actually on teaching. And I've been extremely fortunate to be able to interact with the students in this department who are motivated, bright, and inspiring. And I thank them as well. But at last, but certainly not least, the active research team with Kevin, Zoe, Arno, Pete, Chris, Irena, Emanuele, Gianluca, and Josh, working on a lot of different aspects in the solar system. So take-home message, Aurora is a universal process occurring throughout the solar system. I showed with the cometary Aurora study multi-instrument analysis, which is a key approach to better constrain the given problem, and applying also cross-body comparison, comparing with different, why this phenomenon occurred at this planet and what not, and why not at the other, it's challenging our understanding of plasma physics, and also opening new doors for extrapolating beyond the solar system. Watch out, auroral activity is going to increase in the coming years because the solar activity is increasing. And my last word will be that I've highlighted here a scientific adventure, but after all, it's primarily a human adventure. And I would like to thank very warmly all of those who have participated to it. And let the adventure continue. Thank you very much.
Well, thank you very much, Marina. That was fantastic. The floor is open for questions. If anyone, and Marina doesn't charge much per question. Silence. Anyone who? No? Oh, please. Can you just wait until the microphone comes, please?
I noticed that there was some sort of similarity or crossover between when you were working in Norway with the spectrometer and potentially when you were looking at the Aurora mission of comets. Was that decision to look at the Aurora of comets sort of led by your previous work, or was it very different?
No, it was by chance. I started to look at plasma, and actually it was Paul Feldman, and I was looking at variation in the plasma, trying to actually did a multi-instrument analysis to understand the source and the loss of the plasma. And he said, oh, by the way, on that day, I also see UV brightnesses, which are changing quite similarly to what you have shown here. So it's around, so we went for lunch, and we started to discuss, and it's how the story ended. And at the end, the point was not to prove it was an aurora. It doesn't matter if it turned out not to be aurora. I mean, trying to see if emissions are auroral or not, it's not a goal, but it's allow you to actually investigate plasma interaction in the solar system. So it's a mean. But it was by chance. But it's nice closing of the loop. Yeah.
We'll take another one on the floor. Yeah.
Thank you for presenting really exciting data. In around 2015, there was a discovery made by Indian Space Research Organization. Local magnetic fields were observed on Moon. Is there any data on aurora of Moon or?
On Moon, I mean the terrestrial Moon. I mean, you don't have to have magnetic field or not, but what you do have is an atmosphere. And around the Moon, it's really very, very thin. I mean, there is impact on the surface which generates sputtering, but you don't have really an atmosphere. And that is what is missing. That's the only condition you need is really to have an atmosphere.
From Teams is from Roger. He asks, can Aurora's strength or likelihood on Earth be predicted well?
Can Aurora be predicted on
Yeah.
Earth? Well, that's what the Space Weather Operations Center, I mean, the original one, the one in Boulder that I mentioned earlier, that was actually created with the Human Space Program. Now there are 3 globally, one in Europe and one actually the Met Office Space Weather Operations Center. And all of those centers, yes, they are trying to predict the aurora. Not, I mean, it's useful for auroral watcher, but it's mainly useful for a satellite company to know if there is going to have a big storm or, and is it well predicted? We are well behind compared with the meteorological space weather prediction. So it is improving, but there is still a long way for improvement.
Hi, Marina. Thank you for your talk. Could you comment on some of the structures of the aurora? You have sheet structures, and then you also have these kind of rolled donut structures.
I mean, there is one. Why am I here? There is one. Can I go there? Yeah. So there are one thing is that there is the. Here and on those 2 pictures, you feel that the aurora is converging towards the point, while those ones, they are parallel, and that's just an optical effect. So like you would have in the city, where you are a center of skyscraper, they are converging, the other is parallel. As for the additional structure, sometimes there is on-off, and that can be because the particles have been interacting with waves. And as for the curling, I mean, the precipitation are linked to magnetic field line, and it does then a perturbation in the magnetic field line, though the full, I mean, it's still active research, so. The sheets,
You seem to have one there.
Well, the auroral, I mean, so it's, as I mentioned earlier, that particles can't go wherever they want. So they precipitate in a region which corresponds to the open-closed magnetic field line. So where you're going to see the visible aurora, that's where then you have the most efficient acceleration. Sorry. So acceleration along the magnetic field line, yeah, so you need field line. I mean, usually it's a field line electric field which are going to allow to the acceleration of the particle. So it's on a narrow sheet.
This is a question from Bruce. He asks, how long does a comet-based aurora last? Hours, minutes, days?
All the time, continuously. Its brightness will change with the solar wind activity, but because the solar wind is constant, it's constantly emitted by the sun, it varies in intensity, in energy and so forth, but it's continuously produced by the sun. Then aurora on the for ultraviolet aurora at comets will be always present as long as the comet has a coma, so has an envelope of gas. So when the comet is too far away from the sun, you don't have efficient sublimation, so you don't have any more an envelope of gas.
Do we have any more questions from the floor? Oh, great. Your last opportunity for fame on YouTube for 30 seconds. Please.
Hi, Marina. Very nice talk. So I guess it's always tricky to predict before it launches, but I was curious what kind of result from Comet Interceptor you're personally most excited to get.
Not knowing the target is a tough question. Trying to, well, one is trying to understand the energy transfer and how the different boundaries will be affected at this comet, especially if it's a very dusty one. And beyond plasma physics, of course, as it will be a pristine comet, it's or surface. I mean, it's always pristine in the inside, but pristine on the surface. It will be also interesting to see what the composition will be. Because a comet may have, at Rosetta we detected glycine, which is only amino acid which can be formed in absence of liquid. So it will be interesting to see if also glycine can be, and also the origin of water on Earth. We know it's not primordial because the terrestrial Earth was too warm, so it lost all its water. So water in the ocean has been brought later on. And so far, the D2H ratio is not convinced, doesn't seem to, though there's a lot of, it's a whole, whole story. I will not go into the details of the interpretation of it, but it will be interesting also to know one of the goals is to look in the D2, a heavy to light water ratio for the hydrogen. So that also can provide more insight on the source of water on Earth.
One question here. Can you just wait in the microphone or shout as loud as you can?
For Comet Interceptor, is there a way to detect aurora like there was for Rosetta? What kind of instrument will be able, if the conditions are met to have aurora, how would we see them?
Originally it was, but there was some descoping, so we can follow up offline.
Take one more here.
One more on Teams. Could staring at an aurora on Earth damage your eyes? They're mentioning the ultraviolet component.
No, it's not dangerous. Even though I started with an aurora decapitating a man, no, it's not dangerous. Okay. The one is very dim, it will appear really white, but no, it's not dangerous at all.
Okay, last opportunity from the floor. Okay, is there one more? Okay, that's it. Very well done. Thank you very much.
Thank you very much.
I'd like to call on Professor David Southwood now, who many of you know, and David has been a much valued mentor and advisor to Marina. So, David, please.
So, thank you, Roy. It's a wonderful career you've had, and Marina, looking at the Aurora from a variety of different ways, indeed taking on at one point, the very difficult task of trying to predict when it's going to happen, something that's immensely important, but still a very tricky business. You've worked with some of the real leaders in the field. I was very impressed by your list of mentors. But you've also, I know, given a great deal to them. So please don't take this mentor business too seriously. It's been a two-way traffic, and it's really immensely good to have you here at Imperial. I particularly liked the difficulty you had explaining the sheer emotional experience of seeing the aurora. I mean, it was a nice attempt, but I recommend to all of you, it's one of the only reasons I can think of to visit Norway, Sweden, or Finland. But once you've seen it, just lie there in the snow and look. It is absolutely wonderful. It's actually much slower than the movies. The movies are speeded up by about 10, 15 times. It doesn't matter. It is an extraordinary experience, and I can only recommend it. A long time ago, I started being interested in the aurora, and I could have believed just about everything that Marina told us today, except when I started, the idea of a European spacecraft taking off with a European rocket, going all the way to rendezvous with a comet was unthinkable. And then, even more unthinkable, the idea that you would get aurorae at the comet. I think that's one of the great discoveries of my lifetime. Something completely I would never have thought of or imagined. So it was great to hear your personal history with Rosetta and Philae. And I'm going to close by giving you a poem. I can see a look of horror on about half of your faces. It's, I've thought of it because Marina spent part of her career in the United States, and in particular, she spent part of the time in Massachusetts. And there is probably the greatest poet from Massachusetts is somebody called Emily Dickinson. And for those of you who look shocked, she wrote very short poems. So here you are. I'm going to actually say in the first sentence, there is the word due, which means ode in this case. I'm translating from the French. But morning is due to all, to some the night, to an imperial few the auroral light. Thank you for joining the imperial few, Marina.
Sort of brings an end to the official bit, but probably the good bit is to follow now. There will be a reception outside on level 2 that everyone is welcome to attend. Before we do that, I want to thank Marina for a really wonderful lecture. someone like me who knew nothing about it sat there and thought, hey, I know something about this now. You know, it's really good. So thank you very much. I think we should thank her again and then really celebrate Marina's professorship. Thank you. You can now relax.